Hello, this is for 7.1 Angles of Polygons. I realized that I forgot to actually put a spot for the definition of a polygon on your notes. So at the top, I'm gonna go write it. I'm going to write it out. Polygon. What is a polygon? Not even. Oh boy. Scratch the polygon. We don't want this word. We want diagonal. That's how you spell diagonal. What is a diagonal? We work with diagonals when we're working with polygons. Kind of. A diagonal of a polygon is a segment that joins two non-consecutive vertices. So like how we did the triangle activity before we did the notes, we were using a lot of diagonals to create these triangles that kind of went over a majority of 7.1. Now, if you're watching this and you haven't done this activity, what I just said doesn't make sense. But using diagonals helps form a lot of the theorems that work with polygons. One of the theorems that gets formed is knowing the sum of the interior angles of a polygon, which is our first theorem right here, the polygon interior angles theorem, which states that the sum of the measures of the interior angles. I'm going to rip this paper off. I'm getting sick of the packet. We're ripping the paper. So the interior angles. I'm off screen. God dang it. Of a convex non-gon is, we'll get red. N minus 2 times 180. What is this theorem stating? Well, it says that the sum of the measures of the interior angles of a convex non-gon is n minus 2 times 180. What's a non-gon? A non-gon is just, it's any polygon. A non-gon in particular means it's a polygon that has n sides. Just like if we look at this right here, this polygon has 1, 2, 3, 4, 5, 6 sides. That means this is a hexagon. A non-gon could have 8 sides, which would be an octagon. 18 sides, 27 sides, 167 sides or something. You get the idea. It can be any size polygon, but we can find the interior angles by doing n minus 2 times 180. So if we take into account this hexagon right here, which we counted the sides, so there's 6. So I'm going to write n minus 6 right here because that's what this is. It had 6 sides, so a 6-sided polygon is a hexagon. So I could plug this into the red and find how I can take this right here, the 6, and plug it into the red and find how big that sum of interior angles is going to be on this polygon right here. So I'm going to do 6 minus 2 times 180, and that will give me 4 times 180, giving me 720. This is the total sum of a hexagon. So yeah, And we can do this for many different polygons, and I have 2 examples for you to work through. I probably gave you guys time in class to do this, but not today. This one is going to be done right now. So, how many sides did this polygon have? That's our goal. Not how many sides. What is the sum of the interior angles? We're doing the same process as what we just did right here. So let's count the sides. I'm going to kind of draw out the vertices so I have a better idea of what I'm working with. Now let's count our sides. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 sides. It's a 10gon. I don't know if this has a real name. Place your bets. I bet it doesn't. I'm like trying to pick out what color I want. It's been a long time since I used my pen, so I'm like, ooh, I forget what colors I used to write answers with. So we're doing the same process. Do 10 minus 2 times 180. That's going to give me 8 times 180, which is equal to 1440 degrees. So that's the sum of the interior angles. Great. So this was the same as what we just did up here, but you could have a different question. What if you were given the sum of the interior angles of a polygon already? In our case, we are given that a polygon has interior angles that sum up to 1800 degrees. And we need to classify the polygon by its number of sides. So the sides, what we find in. And I'm given 1800 already. So we're just going to take this 1800 and plug it into like a base equation. We're taking our red up here, this base equation, and we're setting it equal to 1800, pretty much. Because I'm already given this information, that's the sum. And to find the sum of the interior angles, I have to do n minus 2 times 180. So this is my process. I'm just kind of working backwards now to find n. So I'm going to divide both sides by 180 because I need to get n by itself, just like how we do regular work. And this is going to give me a 10 equal to n minus 2. And then I'm going to get that 2 to its other side. And that's going to give me an n equals 12. Perfect. Perfecto. That's all we have to do. Simple enough. I feel this one is nice and simple. Easy. Lovely. Alright. Now, with this theorem, we have a corollary. So this, remember, a corollary works off of a theorem. This one in particular is going to come up next. Well, it's going to pretty much come up for the rest of the unit. I'm going to be real. But it states that the sum of the measures of the interior angles of a quadrilateral is 360 degrees. So, make note that sum of interior angles of a quadrilateral is 360 degrees. Always. I want you guys to write this down because it's going to come up later. Like, when I mean later, I mean it's going to come up in 7.2. And it's good to know that fact. Because we're going to be dealing with a lot of quadrilaterals. Alright. Example 3. Let's find the value of x in this diagram. So, we can just kind of do the same process as we did in example 1. Let's count our sides, and then work from there. So we have 1, 2, 3, 4, 5, 6 sides. So we have a hexagon. Funny enough, we've already done a hexagon example up here, so we know the sum of the interior angles already. But just in case, if we don't know how to do it, we're going to write out steps. Like, what if this was an octagon, per se? We're going to do our n minus 2 times 180. That's going to give me 6 minus 2 times 180. And that will give me 4 times 180, which is equal to 720. What is step 1? It's to find the total, to find the sum of the interior angles, like the total sum. That's step 1. I'll get a different color for step 2. Use black. Step 2. It is to find x. Very basic step 2. But it's kind of laid out for us for what we kind of need to do. We know the angle measures for 5 of these angles on the inside, but we don't know one of them, which is our x. And we know the sum of the whole polygon right here, which is 720. So it comes down to doing 720 equals each one of these. It's 720 equals all of this. So we have x plus 180 plus 111 plus 124 plus 115 plus 145. All of these angles right here add up to 720. And it's just pretty much taking these values right here, moving it to the other side, and that'll give us our x value. If I combined everything on the right, I'm going to end up with x, with 720 equals x plus 613. And then I'm moving that 613 to the other side. And that's going to leave me with an x equals 107. Nice. Cool. Cool. Oh my gosh, there's so much. Ah! I forgot I ripped the paper. It's very much, it is very convenient to have the paper ripped. It's making it easier to write. All right. I will say not all polygons are the same, and it's very important to just know that they're not the same. There's 3 different kinds of polygons. We have one, which is having all congruent sides of a polygon. We have a second polygon that has all of its angles congruent. And we have a third polygon that has all sides and angles congruent. Different names for them. Different names for them. This one right here, the one with all sides being congruent, this is known as an equilateral polygon. Has all of its sides congruent. The one with all of its angles congruent, this is known as an equiangular triangle. Equiangular polygon. Not triangle. Well, I mean, yeah, no. When we learned about triangles, it's just like our triangle concept, pretty much. This is like this would encompass an equilateral triangle. This would encompass an equiangular triangle. This would be both of them combined. This is known as a regular polygon, though. So when all of the sides and angles are congruent on the same polygon, it's known as a regular polygon. When it's only the angles congruent, it's known as an equiangular polygon. And when all the sides and only the sides are congruent, it's known as an equilateral polygon. It's important to know that because sometimes you have to decipher whether something is a regular polygon or not. Like, you might be asked, is this polygon regular? All right, let me check if it is regular. First off, the sides do not look regular at all. They are not the same size. But we're not going to take the sides into consideration at all because we don't need to. We can take a look at the angles on the inside. The three that we do know, they are not the same angle measure. This is 100, this is 140, this is 160. And so right off the bat, this is not, no, this polygon is not regular. It has angles that are different sizes. Cool. All right. If we know that these angles are different sizes, that means it's not regular. But we can still find the information about this polygon, like in B. We're going to find the measures of angle B, D, E, and G. Doesn't matter if it's regular or not. I can still find its angle measures based off of the properties that I already know about polygons, and I know how to find different values of a polygon already. This is kind of like what we did in example 3. So what would make this easy is if I just labeled these all X. Why all of them being X? Well, it's because all of them are congruent. They all have the same angle ring. So that means that these 4 angles are all going to be the same angle measure. Cool. So I can use that to my advantage when I'm trying to find these angles of this polygon. Now, one thing I do need to do is to do step 1, which, remember, step 1, that's finding the total sum of the interior angles. This is not a hexagon, I can tell you that much. So I have to count the sides and angles to figure out what this is. So this is 1, 2, 3, 4, 5, 6, 7. So this is a heptagon. So I'm going to do 7 minus 2 times 180. That'll give me 5 times 180, which is equal to 900. Cool. And now I can set up my equation to find out what X is. So I can do 900 is equal to 100 plus 140 plus 160 and 1, 2, 3, 4 X's. So 4X. And if I combined my like terms, I have 100 plus 140 plus 160. That's going to give me 400. And that's plusing 4X still. If I subtract 400, I'm going to end up with 500 is equal to 4X. Dividing 4 on both sides to get X by itself, I'm going to end up with an X equal to 125. So that means angle B, angle D, angle E, and angle G equal 125. They all equal the same angle measure because they were all congruent. Cool. Simple enough. I guess this was exactly like example 3 still. The only difference was this question, deciphering whether this is a regular polygon or not. So it's okay. Theorem number 2. All right. The polygon exterior angles theorem. This one is also not very bad. It's not bad. You're fine. This theorem states that the sum of the measures of the exterior angles I'm going to get a different color for this one. Of any polygon is always 360 degrees. So that means in our example right here, we have 5 angles. So that means angle 1 plus angle 2 plus angle 3 plus angle 4 plus angle 5 equal 360 degrees. No matter what, no matter how big the polygon is, like it could be infinitely large, infinite many sides. The exterior angles of that polygon will add up to be 360 degrees. Always. It will always be 360 degrees. It will never not be 360 degrees for a polygon. Remember this one. Let's do an example or two. So let's find the value of x in our diagrams. So I can find x right here by adding up 5x plus 58 plus 41 plus 69 plus 35 plus 62 is equal to 360. If I combine my like terms, I'm going to end up with 5x plus 265 is equal to 360. Getting rid of 265. Moving it to the other side, I'm going to end up with 5x is equal to 95. Divide that by 5 to get x all the way by itself. I'll end up with x equaling to 19. And then if I can do the same thing on this side, we have a 2x plus 67 plus 89. That will be equal to 360. Because my theorem states that any polygon will have exterior angles equaling 360 degrees. Combining my like terms, I have 3x. I meant to do plus. 3x plus 156. So adding all my like terms together, that's still equal to 360. Getting rid of my 156, giving me 3x is equal to 204. Getting my x all by itself, so I gotta divide by 3. That's gonna leave me with an x equals 68. Not too bad. Just remember that it will always be 360 degrees. It will never be 361 or 359. Always 360 degrees for the exterior angles being added all up together. More on regular polygons. With the two theorems that we have, we can make specific equations for regular polygons. Remember that regular polygons share the same angle size and the same side length. So, yeah, everything's the same on a regular polygon. So we can make specific equations to make work a little easier, depending on the problems that we get. We can make an equation for interior angles and exterior angles for regular polygons. To find the measures of each interior angle of a regular polygon, we can set up an equation similar to what we've had already for doing interior angles. So n minus 2 times 180. But we're going to set that over n, and that will let us find the measure of each interior angle of a regular polygon. And we can do the same thing for an exterior angle, but instead we just need to do 360 divided by n. And that will get us our measure for each exterior angle of a regular polygon. And we have an example of that for number 6. So we have a trampoline that is shaped like a dodecagon. So we need to find the measure of each interior angle and exterior angle. What is a dodecagon? Well, I believe a dodecagon is 12-sided, but we'll make sure and count. So I'm going to draw in my points to make it easier to count, and then we'll count the sides and then have some fun and do math. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So this is definitely a dodecagon with 12 sides. And that means my n is going to be equal to 12. So let's split up our work and have one be interior angles and have one be exterior angles. So I'll do interior angles over here. So let's do n minus 2 times 180 over n, because that's my equation for regular polygons to find each interior angle. And all I need to do is take my n equals 12 and plug it into this equation. So I'll have 12 minus 2 times 180 over 12. And that is going to give me, simplifying down, 10 times 180 over 12, which will give me 1800 over 12, which will give me my final answer of 150 degrees for each interior angle. And now I'll do it for the exterior angles. I have my base equation of 360 over n. Remember that n is 12. So all I need to do is 360 degrees over 12. And that is going to give me 30 degrees for each exterior angle. And if we want to make sure that both of these measures are correct, all I need to do is add them together and see if they equal 180. And they do. 150 plus 30 does equal 180, because remember that interior angles and exterior angles are a linear pair, so they have to add up to 180. This 7.1 isn't too bad. I hope the homework is nice to you, and I'll see you in 7.2.